The universe is a vast tapestry of wonders, and among its most captivating threads are pulsars and neutron stars, celestial objects that defy imagination with their extreme properties. At the heart of this exploration is Pulsar J0952-0607, a cosmic enigma that spins at an astonishing 707 revolutions per second, outpacing the blades of a helicopter or a household blender. Despite its colossal mass, nearly 2.5 times that of our Sun, it is compressed into a sphere small enough to fit within New York City's limits. This video embarks on a journey through the mesmerizing world of pulsars and neutron stars, unraveling their origins, mechanics, and the profound implications they hold for our understanding of the cosmos. Pulsars are a subset of neutron stars, renowned for their breathtaking rotational speeds. For Pulsar J0952-0607, this rapid spin is fueled by a dramatic interaction with a nearby white dwarf, a stellar remnant left after a star exhausts its nuclear fuel and sheds its outer layers. Orbiting dangerously close, the white dwarf falls victim to the pulsar's relentless gravity, which tears away its material. This stolen matter spirals inward, carrying angular momentum that accelerates the pulsar's rotation. As the pulsar gains strength, the white dwarf weakens, losing mass until it may eventually fade into the cosmic abyss. This interplay is a testament to the universe's capacity for both creation and destruction, powering the pulsar's extraordinary spin while dooming its companion. Neutron stars emerge from cataclysmic events that mark the end of massive stars, those at least 8 times the mass of our Sun. When such a star depletes its nuclear fuel, its core succumbs to gravity's crushing force, collapsing in on itself. This collapse ignites a supernova explosion, a dazzling outburst that briefly outshines entire galaxies. What remains is a neutron star, a dense core where extreme physics reigns. With a typical mass of 1.4 solar masses packed into a diameter of just 12 to 15 miles, their density is staggering. A mere teaspoon of neutron star matter would weigh 1 billion tons on Earth, equivalent to 3,000 Empire State Buildings or the collective weight of humanity. Neutron stars are realms of extremes. Their surfaces scorch at up to 1 million degrees Celsius, and in the fiery aftermath of their birth, temperatures can spike to 10 million degrees, 800 times hotter than the Sun's surface. Remarkably, this heat doesn't melt the star. Instead, a solid crust, likely made of iron and about 0.6 miles thick, encases it. Beneath this shell lies a realm of speculation. The immense pressure may fuse protons and electrons into neutrons, and some scientists propose that these neutrons could dissolve into quarks, forming a state of matter unlike anything on Earth. The gravitational force of a neutron star is equally awe-inspiring. Escaping its pull requires a velocity of 93,000 miles per second, nearly half the speed of light. This intensity means that even a lightweight object like a feather dropped onto its surface would unleash energy akin to 1,000 hydrogen bombs upon impact. Such power underscores the neutron star's role as one of the universe's most formidable objects. The Pulsar saga began in 1967, when British researchers detected rhythmic radio signals from space, so precise they were initially mistaken for extraterrestrial messages. These pulses were soon traced to neutron stars, dubbed pulsars for their pulsating emissions. These stars emit beams of radiation, radio waves, visible light, X-rays, and gamma rays from their magnetic poles. As they rotate, these beams sweep across the cosmos, creating a lighthouse-like effect observable from Earth. A pulsar's swift spin stems from the conservation of angular momentum. As a massive star collapses into a neutron star, its diameter shrinks dramatically, boosting its rotation speed. much like a skater pulling in their arms to spin faster. Some pulsars, including J0952-0607, amplify this effect by siphoning material from a companion star, adding momentum to their whirl. These stars emit intense energy beams from their poles, and their rotation makes these beams detectable as regular pulses. This precision is so reliable that pulsars serve as cosmic clocks, rivaling atomic timekeepers and aiding in tests of fundamental physics. Pulsar J0952-0607 stands apart with its 2.4 solar masses and 707 rotations per second. It teeters near the theoretical mass limit, around 2.5 to 3 solar masses, beyond which gravity would overwhelm it, triggering a collapse into a black hole. Its rapid spin generates centrifugal force that resists this fate, but the balance is tenuous. If it fully consumes its white dwarf companion, the added mass could tip it over the edge, transforming it into a black hole. The might of a pulsar like J0952-0607 poses a cosmic threat. If it materialized near Mars or Jupiter, its gravity would shred the closest planet, disrupting the solar system's harmony. Planets would veer off course, drawn toward the pulsar's maw. Earth's atmosphere would vanish under intense radiation, leaving a barren, scorched surface. Ultimately, the sun itself could be devoured, and the pulsar's collapse into a black hole would erase our solar system entirely. A mere 1,000 light-years away, the Velar pulsar dazzles as one of the brightest known pulsars. Its gamma radiation is 200 times more potent than that of typical pulsars, a mystery that scientists attribute to possible particle acceleration in unusual regions or amplified magnetic fields. A puzzle still unfolding. Magnetars, a rare neutron star variant, boast magnetic fields 1,000 times stronger than those of standard pulsars. Formed in just one of every 10 supernovae, their magnetic might can warp atomic structures. A human too close would disintegrate at the atomic level. Magnetars also undergo starquakes, where their crust fractures, unleashing energy bursts detectable galaxy-wide. Pulsars endure for billions of years, sometimes weaving unexpected tales. Some, like PSR B257+12, with its 3 super-Earths, or PSR J0952-0607, with 2 massive exoplanets, host planetary systems. These planets trace elliptical orbits, hinting at chaotic origins far removed from our solar system's orderly paths. In the universe's infancy, quasi-stars may have reigned as colossal entities, possibly powered by black holes at their cores. These giants could have dwarfed modern stars like Scuti, collapsing spectacularly to seed supermassive black holes at galactic centers. Though extinct, their influence might persist in primordial black holes drifting through space, or even hypothetically within stars like our Sun, though evidence remains elusive. Pulsars and neutron stars are more than celestial curiosities. They are keys to unlocking the universe's deepest secrets. Their extreme gravity, blistering spins, and exotic compositions challenge physics and illuminate cosmic evolution. From J0952-0607's delicate dance with collapse to the Velar pulsar's brilliance and Magnetar's magnetic fury, these objects captivate and inform. As science advances, they promise to reveal even more about the vast, wondrous cosmos we inhabit. Pulsars are not fleeting sparks in the cosmic night. They are enduring sentinels, capable of persisting for billions of years. This remarkable longevity allows them to bear witness to rare and extraordinary events, sometimes even shaping the universe around them. Among their most surprising feats is the ability to host planetary systems, defying the notion that planets belong only to stars like our Sun. These cosmic survivors, born from the ashes of stellar cataclysms, continue to reveal the universe's capacity for the unexpected. Consider the pulsar PSR B257+12, nestled 2,300 light-years away in the constellation Virgo. This neutron star is orbited by 3 super-Earths, planets with masses several times that of our own. Unlike the nearly circular orbits of our solar system, these planets trace highly elliptical paths, a clue to their chaotic origins. Perhaps they formed from debris scattered by the supernova that birthed the pulsar, or maybe they were rogue worlds captured by its gravitational embrace. Similarly, Pulsar J0952-0607, located in the constellation Vulpecula, hosts at least 2 exoplanets, each far more massive than Earth, also carving elliptical orbits. These peculiar systems challenge our understanding of planetary formation, showing that even in the harsh environment of a pulsar's radiation and gravity, worlds can endure. The study of these orbits, stretched and skewed by the pulsar's influence, offers a window into the violent histories that shaped them, reminding us that the cosmos is a place of relentless reinvention. The longevity of pulsars also makes them ideal laboratories for probing the universe's fundamental laws. Over billions of years, their steady pulses serve as cosmic metronomes, allowing scientists to test theories of gravity, detect gravitational waves, and even map the distribution of dark matter. For instance, slight variations in the timing of a pulsar's pulses can reveal the presence of unseen companions or ripples in space-time caused by distant black hole mergers. This precision has turned pulsars into tools for exploring questions that reach beyond their own existence, from the nature of gravity to the structure of the cosmos itself. To understand the universe's earliest chapters, we must turn to a hypothetical class of celestial giants known as quasi-stars, which may have blazed in the infancy of the cosmos. These behemoths, if they existed, were unlike any stars we know today. At their cores, they likely harbored nascent black holes, which acted as both power sources and structural anchors. This unique anatomy allowed quasi-stars to swell to sizes that dwarf even the largest modern stars, such as Ui Scuti, which spans 1,700 times the Sun's diameter. A quasi-star could have been so vast that, if placed in our solar system, it would engulf the orbits of Jupiter or beyond. The black hole at a quasi-star's heart fed on the star's material, driving ferocious energy output that inflated the star to immense proportions. This process, however, was a prelude to a dramatic end. As the black hole consumed the star from within, the quasi-star would eventually collapse in a spectacular implosion, potentially giving rise to the supermassive black holes that now anchor galaxies like our Milky Way. These collapses could have scattered heavy elements forged in the star's core across the early universe, seeding the formation of future stars and galaxies. The idea of quasi-stars, though speculative, offers a compelling explanation for how supermassive black holes formed so quickly after the Big Bang, a puzzle that continues to intrigue astronomers. The study of quasi-stars also prompts us to consider the universe's first light. In the dark, turbulent era following the Big Bang, these giants may have been among the earliest objects to illuminate the cosmos, their brilliance piercing the primordial fog of hydrogen and helium. Their explosive deaths would have left ripples in the cosmic microwave background, faint echoes that modern telescopes, like the James Webb Space Telescope, are now seeking. By piecing together these clues, scientists hope to reconstruct the universe's formative moments when the seeds of galaxies were sown. Though quasi-stars are long gone, their legacy may linger in subtle ways. One intriguing possibility is the existence of primordial black holes, tiny relics of the universe's birth. Formed in the chaotic conditions of the early cosmos, perhaps during the same processes that birthed quasi-stars, these black holes could still drift through space today. Some might be no larger than a grain of sand, yet possess the mass of a mountain, making them elusive but potent. Occasionally, these wanderers could become trapped within gas clouds or even inside stars, altering their hosts in ways that astronomers are only beginning to explore. In a more speculative vein, some theorists propose that a primordial black hole could lurk within a star like our Sun, a hidden passenger from the dawn of time. Such a black hole would be minuscule, smaller than an atom, but its presence could theoretically influence the star's behavior, perhaps by subtly altering its fusion processes. Current observations of the Sun, however, show no signs of such an anomaly. Its spectrum, energy output, and magnetic activity align perfectly with models of a standard main-sequence star. Still, the idea sparks curiosity, reminding us that the universe may harbor secrets we've yet to uncover. These cosmic remnants, whether primordial black holes or the chemical signatures of quasi-star explosions, offer a bridge to the past. By studying them, we gain insights into the processes that shaped the universe's evolution, from the formation of the first stars to the assembly of galaxies. Missions like the European Space Agency's Euclid telescope, which maps the universe's large-scale structure, are helping scientists trace these ancient influences, revealing how the echoes of the cosmic dawn resonate in the modern cosmos. As we journey deeper into the cosmos, pulsars and neutron stars continue to challenge our understanding of the universe. These celestial objects, with their extreme densities, blistering spins, and gravitational might, are not just remnants of stellar death. They are gateways to unraveling the universe's most profound mysteries. Yet, for all we've learned, many questions remain tantalizingly out of reach, beckoning us to explore further. One of the greatest puzzles is the inner composition of neutron stars. While we know their surfaces are encased in a solid crust of iron, the depths below remain shrouded in mystery. Are they filled with a soup of neutrons, or do exotic states of matter, like quark-gluon plasma, dominate? Future missions aim to decode these secrets by studying X-ray emissions from pulsars, bringing us closer to understanding the fundamental behavior of matter under extreme conditions. Another frontier lies in the potential for pulsars to reveal hidden dimensions. Theories like string theory suggest extra spatial dimensions beyond the three we know. Pulsars, with their precise timing, could serve as probes for these ideas, offering clues through unexpected signals. While speculative, this possibility keeps scientists pushing the boundaries of discovery. The future might also unveil new types of neutron stars, like quark stars, made entirely of deconfined quarks. Detecting one would confirm a new state of matter and open a window into the strong nuclear force. Pulsars and neutron stars, then, are more than cosmic wonders. They're the universe's laboratories, testing physics and hinting at what's yet to come. What captivates you? Before we end, let's reflect on these stellar marvels. Pulsars and neutron stars blend beauty and mystery, telling tales of cosmic survival and transformation. Now, your turn. What fascinates you most about pulsars and neutron stars? Their extreme densities, their cosmic precision, or something else? Share your thoughts in the comments. I'd love to hear from you. Ever wondered if the universe loops endlessly? The evaporating model suggests it does, with cycles of big bangs and big crunches creating new cosmos from old. It's a wild idea that redefines time and existence. Curious? Click here for our previous video, which is suggested above, to explore the evaporating model and its cosmic twists. If you enjoyed our content, don't forget to like the video and share it with your friends. Thanks for watching.